A relation like subset or less than is said to be non-symmetric. We'll talk more about this later, but it's useful to introduce the term now. If we know that A is a subset of B, we can't claim that B is also a subset of A. So if we want to prove A is a subset of B, we don't have to worry about B subset of A. On the other hand, equals is symmetric. If A equals B, then B equals A. And this means we must prove both directions. Now, that means different things in different contexts, but in practice, for sets, we rely on the theorem, if A and B are two sets, A equals B if and only if A is a subset of B and B is a subset of A. Note this is a biconditional, so it's really a conditional and its converse. If A equals B, then we have the subset relationship, and if we have the subset relationship, then A equals B. We'll prove this by assigning it as a homework problem. But assuming that we have proven the theorem, let's try to see how it plays out. So let's prove that the union of the intersection and the difference is the set. While a Venn diagram cannot be used to prove statements, it can guide our proof. If we draw the Venn diagram, we see that it appears to be true that the set A consists of two parts. The part in both sets, that's the intersection, and the part in A but not in B, that's the set difference. This suggests a proof by cases as we consider the two parts separately. So remember, the last line is what you've actually proven, and so we can actually write the last line. And now the value of a biconditional or a definition is that they can be used to go forward or backwards in a proof. And since this is the last line, we want to be able to go backwards. And we do have a biconditional we can use. If we can show that one is a subset of the other, we can then conclude that they are equal. Now, to get to this line, which is our next to last line, we do need to show that each is a subset of the other. So we actually need to do two sub-proofs. We want to show that A is a subset of the union. So again, the last line is what we've proven, so we'll write that as our last line. Now remember, definitions are the whole of mathematics. All else is commentary. To show that one set is a subset of the other, we need to show that any element of the one set is also an element of the other. So let's start with some element in A. Now, if we go back to our Venn diagram, we see that it's going to either be in this intersection or it's going to be in the set difference. And what that means is that either this element is in B or it isn't. So remember, you can assume anything you want as long as it's explicit. So let's assume that X is in B. So definitions are the whole of mathematics. All else is commentary. If X is in B and X is also in A, then X is in the intersection. Again, definitions are the whole of mathematics. Since X is in the intersection, it's going to be in the union, which completes our proof as long as X is in B. Now, it's important to note that we could stop our proof here. It wouldn't be complete, but it would be correct as long as we included the additional premise. The phrasing would end up being somewhat awkward, and we'd have to state it as something like, if for all X in A, we have X is in B, then A is a subset of the union. And it's worth pointing out that sometimes you can only prove one case, and that's still a result even if it's not what we wanted. But let's consider our second possibility. Suppose X is not an element of B. So definitions are the whole of mathematics. All else is commentary. That's what's required for X to be in the set difference. So again, that means X is in the union of the two sets. Putting the two parts together, if X is in A, then whether or not X is in B, X is going to be in the union, and so every element of A is an element of the union, and so A is a subset of the union. Now we do need to go the other way, so let's consider an element of the union. And so either X is in the intersection, or it's in the set difference. Suppose it's in the intersection. Then, because it's in the intersection, it has to be in both sets, so it has to be in A. On the other hand, suppose it's in the set difference. To be in the set difference, you have to be in A as well, so whether it's in the intersection or the union, it's going to be in A. And so we have the union is a subset of A, and A is a subset of the union, which completes our proof.